So yeah, next section, we'll be talking about the course logistics. So then the goal of our course is to teach students the fundamentals of blockchain development, the Solidity programming language, as well as industry relevant tools such as MetaMask, Infura, Truffle, and Ganache, so that students will be equipped with industry relevant experience in an accessible and collaborative environment. We'll be going over more practical aspects of blockchain, so students will be able to develop their own blockchain applications. While we will go over blockchain fundamentals, we won't be delving too deep into the theoretical aspect of blockchain, which would be more for the blockchain fundamentals decal. So then our course will be for 1 unit. We would be emailing everyone a class code after this lecture. It would be from Thursday, 6 p.m. to 8 p.m. on the same Zoom link. We would have recordings posted after every lecture in case we would have recordings after every lecture in case you aren't able to make the class. So then me, Nathan Zhang, and Solomon Joseph would be the course leads, and we have these facilitators. Our email is devdecal@blockchain.berkeley.edu. So then here is what topics we'd be covering each week. So during week 1, we'd be covering Introduction to Blockchain Development, which is what we're doing now. Week 2 would be Solidity and Developer Tools. Week 3 would be Solidity Syntax. Week 4 would be Web3.js and interacting with Ethereum. And week 5 would be Security, Token Development, and Wallets. And then after that, we'd be covering DApp Architectures Part 1, and the Decentralized Application Architectures Part 2. And then we'll cover Scalability, Interoperability, CK snarks. And then we have some special topics with guest lecturers on different topics such as Bitcoin development, Ethereum ecosystem, as well as Truffle and Polkadot. So then our course, because we'll be developing applications, will require you to have some background in computer science and programming. At the bare minimum, we hope you've taken CS61A, but it's recommended to also take CS61B as well. Our course will be teaching Solidity, JavaScript, and Python, but you won't need to have any experience in either Solidity or JavaScript. And then many of the concepts we'll be going over would probably be new and difficult for you. So don't be hesitant in asking for help. You could reach us through Piazza as well as through the email. Grading would be pass, no pass for this course. And in order to pass the course, you would need to submit all your homework, save 2 to 3 assignments. And I'll talk more on that later, and also complete the final project. We will be grading on completion, but then if you want to learn more about developing blockchain, it's highly recommended that you put effort in the homework and projects. So then I'll talk more about homework. So then there'll be homework dispersed throughout the course to further your understanding of the concepts that are taught in lecture, and they'll be based on the topics taught during the previous lecture, and they'll be due before next week's lecture. We will be grading based on completion, and if you attend all live lecture, we'll grant you another homework pass. And homework will be posted weekly on the course's GitHub repository, which we will also post on Piazza. And this class is asynchronous, as recordings will be posted on Piazza and the course website. Live lecture is from 6 o'clock to 8 o'clock p.m. every Thursday, which is the same time as the fundamentals decal. You are welcome to attend both because we'll be posting recordings, and we'll do our best to understand and accommodate any extenuating circumstances that you might have. So then we'll also have a final project for this course, which is something new that we're doing for the first time. And if you're familiar with CryptoKitties, which is an Ethereum-based game. It'll be something similar, but we'll be basing it on different pictures of OSCE. The completion of the project is mandatory if you want to pass the class, but if you have any concerns about the project, please let us know. So here are just some expectations for the course. Expect from the course staff a review of theoretical blockchain concepts are essential for understanding the developer side. While we may not go too deep into fundamentals territory, we will give you the background of blockchain needed to code a blockchain application. We will give technical in-depth talks that go as far down to the code that is written for the decentralized apps, and rewarding but difficult programming assignments. Like the workload for this class wouldn't be too bad, but then they would be somewhat frustrating because this is a new technology and there's just not that much done on it yet. But then if you have any concerns, let us know and we will be as understanding as possible. So then on Zoom, turn cameras on or off. We're not too picky on that, but the microphones should be off. Chat is reserved for questions to the lecturers and nothing else. And also try to limit your background distractions if your cameras are on. So then don't cheat. If you cheat, you'll automatically fail the class. And also don't try to enable others to cheat. So don't post your solutions on public repositories like GitHub or GitLab. If you have any questions about any of the homework or the project, feel free to contact any of the course staff. So I'll be handing it over to Ayush to talk about blockchain and Ethereum and give a quick overview on these topics.
Awesome. Thank you, Nathan. Hello, everybody. I'll go ahead and share my screen. Let me switch off here. Let's see. So yeah, before we get into this, any questions on the course policies, structure of the course, anything like that? Want to get those answered and have them not hanging. So yeah, any questions on that stuff? How many hours of work per week do you expect? So I would say not too many. This is a 1-unit course. We designed it, considering it's a Corona semester, it's online, everything's different. So the homeworks should not be too hard. The project itself should not be too hard. You'll have multiple weeks to work on it and the entire Blockchain at Berkeley education team to support you. So I would say maybe 2 hours a week, lecture plus 1 to 2 hours a week of homework on top of it. Will we have homework parties? That is a good idea. We should have homework parties. If you want to do that, we will organize it. And yeah, Nathan can answer the fundamentals dev questions. So you should be able to take both. You can show up to one of them. I would say the head of education of blockchain, Janice, she was here for a while. She said, if you are enrolled in both, it is better to come to these lectures for the dev decal instead, because we are actually going to bring in industry speakers into this decal. We're going to give you live demos in this decal. So coming to this decal will be a lot more fun than like a normal CS 162 class. I'm currently in 162, so but it'll be fun to come to these lectures. So I think you should try to attend in person if you can. If you don't get in, both decals are open to an audit. As always, we don't want to close off content to anyone just because. So if you're interested, just show up. The link is sent to you. You have the link. So feel free to come. Cool. We good? Awesome.
Yeah, sorry, before you begin, just another thing, if any of you guys are dual enrolled in other decals or you have some conflicts, please be sure to fill out the Google form that's in the Piazza post, and we will be handing out enrollment codes shortly after this lecture.
So, okay, so I know this class, I know Nathan had just said you don't have to turn your camera on. I will politely ask you if you're comfortable to turn your camera on, because I just like seeing people's faces when I lecture. It's a lot more fun. And I think I've kind of emailed back and forth with some of you, so it'd be just nice to like say hello, say hi, kind of on Zoom. So yeah, go ahead, turn your camera on if you're down. It'd be just dope to see all of you. Thank you. Appreciate it, guys. So I'm about to begin. We're going to go over blockchain fundamentals and Ethereum fundamentals. And if you have any questions, send them in the chat. Feel free. I will keep the chat window open, so don't be afraid to ask any questions. I'll try my best to cover everything. Cool. So let's get started. Let's go. Blockchain and Ethereum overview. So starting off with the blockchain review. Quick definitions. Blockchain versus cryptocurrency. What is the difference? So a cryptocurrency is a completely digital, formless currency that is tied together using computer science, crypto, and economics. And those three components is what makes a blockchain, which is the data structure behind cryptocurrency. And a blockchain is a method of storing data amongst multiple parties. And there's many properties to blockchains that make them like trustless and decentralized. So you can think of the two related, such that cryptocurrency is what drives the economic incentives that keeps blockchain systems alive and functioning well properly. So yeah, don't conflate the two. They are separate things, but they're also related to each other in that way. Insofar as cryptocurrencies are arguably necessary for blockchains to do their purpose, serve their decentralization purpose. So what is a blockchain? A blockchain, in my own personal one-sentence explanation, is a blockchain is a heavy data structure that enables coordination at scale of many different parties without trust. You rely on the code of the blockchain instead of relying on a third party to facilitate who owns what and who gets what. But going more academically, there is actual properties of the blockchain that we can assume. So one is immutability. Because we use hashing in cryptography, hash functions are very sensitive. They're one-to-one. So every input has their own output. And if you change the input even a little bit, the output will change drastically. So, and we'll go over this later again. So we use that sensitivity test to determine the immutability of a blockchain. It's very evident if anything has been tampered on the blockchain because of this cryptography. A blockchain is also a distributed ledger. So it's a ledger that is shared by many different people. Everyone holds a copy of it. It's decentralized. You rely on the proof of work or proof of X consensus to validate what goes on the chain, on the ledger. And there's no central authority, no institution that does that for you. And the way that works is through consensus. You have different servers, different people running a consensus protocol so that they all agree on what to put on the next block in the chain. So that was your 2-slide crash course on fundamentals. So if that was a little bit too quick, go ahead and look at the fundamentals decal lecture 1, lecture 2. That gives a very good, more in-depth explanation of like the system design theoretical stuff. In this course, we are going to focus on actually building in code, building applications on Ethereum. So let's go into Ethereum, which is the blockchain that we will focus on in this course. So what is Ethereum? Ethereum is a decentralized blockchain, that's kind of like a synonym, platform designed to run smart contracts. You can think of it like the world's big distributed computer. It's a big state machine to hold transactions. And when you make a smart contract on Ethereum, you are changing the global state. So when you have like an application built on Ethereum, what that means to build on top of Ethereum is to basically have an interface like a website that changes the state of what is on the Ethereum blockchain. So once you get that concept in your head, that unlocks basically the key to how you design decentralized applications. You can rely on this Ethereum blockchain to be your state machine, to be like your big backend that everyone can see. So yeah, a transaction to the Ethereum blockchain is like a state state transition function or state transaction function. And Ethereum has a native asset called Ether or ETH, which we'll get into. And that's what you'll have to use to drive your applications. Some examples of these decentralized applications, or DApps, or Dapps, as we call them. Augur is a prediction market. There was a prediction market for, will Donald Trump win the election? And I think like 65% of the total pool said no. And that was more accurate than a lot of the CNN polls that were put up. And that's kind of a big concept in blockchain, is like the libertarian idea that markets are more efficient and more accurate than just vague surveillance of the public. There's also CryptoKitties, which is like a trading card games for really cute virtual cats. We did a consulting project for them recently. They trade NFTs, which we'll do in our project. An NFT is like a token that isn't really money, but it's like a token that represents a specific item or a specific like thing that you own when you own the NFT token. They're like a unique token. So yeah, these are like two examples of pretty cool applications, kind of out there applications on the Ethereum blockchain. Like a derivative. There are derivatives. You can, if you're interested in that, there's like decentralized finance. This is not a derivative because it's like a real thing, but there are derivatives, and you can own derivatives on blockchain platforms. It's very cool. It's called decentralized finance, DeFi. So I'm sure a lot of you are kind of familiar with Bitcoin. That's like the most popular blockchain that everyone knows. So kind of comparing Ethereum versus Bitcoin. Bitcoin on the right is a decentralized asset. It's simple and robust. Uses a stack-based language. It's not supposed to be Turing complete. But Ethereum, on the other hand, is created so that you can use it as a computer, as a machine. It comes with a Turing complete scripting language called Solidity. And we're going to be learning Solidity in this course and actually making applications using Solidity. So Bitcoin uses UTXOs for transactions. Ethereum uses accounts, which are simpler, arguably. It uses a ETH hash mining instead of SHA-256. So it has a bit of a smaller block time. But if that doesn't mean anything to you, don't worry about it. So let's go over how Ethereum uses accounts. This is actually important. So UTXOs versus accounts. A UTXO in Bitcoin stands for an unspent transaction output. The transaction sends an output from the previous transactions, and it generates new outputs for transactions in the future. What does that mean? UTXOs are kind of like a change-making system for Bitcoin. So your balance is the sum of your UTXOs. Every Bitcoin address has a set of UTXOs that are associated with it. And your balance is like the sum of these UTXOs. So when you pay someone, you're like sending them UTXOs, essentially. That's the very simple way of thinking about it. Just like paper bills. Like if we didn't have banks, like your money would just be the number of bills in your wallet. So you could only pay someone in a $100 bill if that's all you had, and they'd have to give you some change back. So Ethereum does not take this approach necessarily. Ethereum uses accounts. So with Ethereum, you can think of it more like the credit card scenario that we're used to. An account has a state and a 20-byte identifier. So if you see that hash, or not hash, but that hex digit, that's like an example of an Ethereum account. So that is your identity on the Ethereum blockchain. And there's two types of accounts. There's externally owned accounts, which are like the users, the people in Ethereum who control, they have their own private keys and they have no code associated with them. But then there's also contract accounts, which are smart contracts. And those are controlled by the code that is in the smart contract. So you can actually send Ether to a smart contract. And that concept drives the entire Ethereum ecosystem. Okay, yeah, let me see if there's any questions. Like Coinbase. Okay, so good question. Coinbase holds all of your externally owned keys. Coinbase is like one layer above this, if that makes sense. Like Coinbase is like an interface that you can use to interact with your externally owned keys, and you can send your Ether or your Bitcoin or your Dogecoin or your whatever XRP to whatever address you want. So Coinbase like handles that for you. This layer is actually the blockchain layer itself. So it's like one layer below Coinbase. And in this layer, like Ethereum itself has contract accounts and externally owned accounts, which are like the user accounts. So I get that it's a little bit convoluted to think of at first, but the main difference between Coinbase and like these accounts is that Coinbase is the one that would be interacting with these accounts. Whereas in this course and in Ethereum generally, you just interact with the addresses directly yourself. You keep track of it all yourself. So this is the way that like blockchain is intended to be used, is that you kind of keep your own custody, where Coinbase kind of gives you like an easy way, one-click way to do it. I think that's a good way to explain it. Cool. So one more question. Can you send money in Ethereum too? Yes, you can. What's the difference between Ethereum's version and UTXOs? Okay. So don't worry about UTXOs. If you're curious about UTXOs, watch the Bitcoin fundamentals lecture, lecture 1 or 2 of the fundamentals decal. For Ethereum, you very much so can send money. Ethereum is money, right? So you can send your Ethereum from one address to another address. You can send your Ethereum from a user address to a contract address. The whole system is built around the idea that you can send ETH back and forth on the ETH blockchain. And not only ETH, you can also send Ethereum tokens like NFTs that are offered on Ethereum, other coins that are offered on Ethereum. So Ethereum is a very diverse ecosystem of assets, and you can send any compatible asset to any address on Ethereum. Very, very big ideas here. So yeah, don't feel the need to wrap your entire head around it right now. It'll come over time. So this is a little bit more into the granularity, but what is stored in an account state? In an account, there's a nonce, which is basically the number of transactions that are sent from that account, and then a number of contracts created if it's a contract account. That's used for cryptographic purposes to provide a randomness to the hashing, and it allows for more distributed hashing and security, basically. So that it's like a security thing. There's also balance, which is the important part. It's the number of way, which is ether. One way, or 10 to the 18 way, is one ether. That's one of the beauties of cryptocurrency, is that it's so divisible. You can't split up $1 into 10 to the 18th of $1. The max you can go is 1 cent. But in crypto, you can do this. There's also a storage root, which is the identifier to the storage of the contract, and there's a code hash, which is the code of the contract that's hashed. So depending on what type of account it is, these are the parameters that are stored in the account. And now let's talk about to the previous question of the UTXO model versus the Ethereum model. In the UTXO model, you encourage users to use a new address for every transaction received. And it's harder to link accounts to real world identities because you have to trace these UTXOs back and forth. It also allows for scalability because you can process multiple UTXOs concurrently, and that enables parallelism in the Bitcoin system. But for the account model, there's also benefits as well. You only need to update one balance instead of storing every UTXO and making change. So the algorithm is a lot simpler, and it uses a lot less space. As you can see, 300 bytes versus 30 bytes. When you multiply that times millions, even billions of accounts, that really adds up. And then finally, it's just simpler. I don't like the UTXO model is very convoluted, and this account model is far more intuitive. You just tick the balance up or tick it down. It's very nice. So that helps you, the developers, to program your smart contracts. Cool. Any questions so far on that stuff?
Oh wait, I'll be honest. Like this is difficult to grasp in like 30 minutes, right? So like you said, this stuff is covered more in depth in the fundamentals. Like, can we get like a link to the course website? I'd like to watch it more in depth later on.
Sure thing. So yeah, I think what we can do is on the website as well, we'll upload like a link to some of the slides that go over this stuff. We can do that. Cool. And then one question is, does the simplicity aspect of Ethereum suggest it may outdo Bitcoin in the long run? Good question. I cannot answer that because that is an opinion. So academically speaking, it's hard to tell. My personal opinion is that like it's possible, but it's not really an apples to apples comparison. Yeah, exactly. As Meet just said in the chat, it's not really an apples to apples comparison. Like Bitcoin is meant to be a currency with a fixed supply, and Ethereum is meant to be like a logic programming layer to things. So I kind of see them as two different things that go in the same direction. Security-wise, UTXO is probably better system-wise because I think you have there's like a couple reasons for that, but it's like a marginal difference. The chance of something bad happening is a very, very low probability for both. So security-wise, they're pretty similar. There are some security flaws with the account model that has caused hacks in the past, but now smart contract developers know how to bypass these things. And every time there's a hack, the community keeps learning to do better. So that's that. Yeah. So yeah, so don't worry if that stuff went over your head. It's definitely a lot to throw at you in just a short amount of time. But if you're going to pay attention to one thing, I think gas is the thing that you should pay attention to. So gas is basically what drives the entire economic system of Ethereum. So it's not free, basically, to use Ethereum. Like it's a decentralized network, and the benefit of using a centralized system. So even when you use Coinbase or use like a bank, you have to pay fees to the bank because they have, they have to do work to like process your transaction and all that. So a decentralized system is no less. Like someone has to pay for the work that is being done, even if it's just like a protocol that is using energy. That fee that we pay is the gas. So gas is the fee that's incurred for every computation that results as a result of a transaction. So if you're the sender, you pay gas to have your transaction go through. And that ensures that the network isn't misused. For example, if you're familiar with the denial of service attack, you can't spam transactions in Ethereum because you'll have to pay gas for every transaction. So you can't just you can't just clog it up. And who are you paying gas to? So I think we'll go over that. So you pay gas to, it's like the miner's fee. Yeah, it'll eventually go to a miner who's the one who's validating your transaction, the one who's actually doing the computation. They'll receive the reward, which is your fee. Yeah, good job, guys. So continuing on, why do we need gas? It allows for parallel and distributed computation. So any transaction on the EVM, which is the Ethereum virtual machine, requires a large amount of computation. And this is why smart contracts are best used for simple tasks. So you can't write like a full game in smart contracts. But you would write maybe a game in like a traditional way and then have a component of the game that interacts with Ethereum through a smart contract. So when you're designing your blockchain applications, the point isn't necessarily to design the entire thing on a blockchain. The point is to use a blockchain effectively to enhance your product or enhance your idea. That's for some cases. In some cases, you do want the entire thing to be decentralized. So you use other things like IPFS for decentralized file storage and all that. And the second reason is it allows for Turing completeness. So we can have loops now. And if you're familiar with CS70 and the halting problem, we can solve that using gas. So it's impossible to determine ahead of time whether a given contract will terminate. And that's the CS70 halting problem. So with gas, if you had like a while true loop in Solidity, it won't actually go forever because at a certain point, the contract sender will run out of gas. So that is like the terminating factor. So you can guarantee that a program will terminate because it'll probably run out of gas at some point, like a car. So that is a really beautiful system as to why Ethereum is possible, is because of gas. And you cannot abstract this away. Many people in this industry have tried to like make apps on Ethereum that, oh, the user shouldn't know about blockchain, the user shouldn't know about gas, the user shouldn't care about these things, but you simply cannot abstract these things away because they are so foundational to the way that this works. So that it's I like this. I think it's beautiful. So yeah, just going on. Gas basically measures the work necessary to perform a transaction. For example, one KECAC 256 hash costs 30 gas and then 6 gas for every 256 bits of data. The Ethereum yellow paper covers this in more detail. There's a gas limit, which is the maximum amount of gas the user is willing to spend. This is something that you say upfront when you're sending the transaction. And there's a gas price, which is the amount of ether you're willing to spend on every unit of gas. So this is where it's a little bit confusing. So listen to the difference between these two. The gas limit is like, as it says, the amount of gas you're willing to spend maximally. But the gas price is actually how much ether, so the value of gas you're willing to spend, or the value of every unit of gas you're willing to spend. The gas price is what determines your priority of your transaction getting computed in the network. So if you have a higher gas price, or a higher gas limit, rather, your transaction will be of higher priority for the miners. Gas price, is not really up to you; it's up to the network, based on the volume of transactions going on in the network. So right now the gas prices are pretty high, so it does fluctuate. It's like the gas price is a market. Cool. So how does this actually work in reality? With every transaction, the sender specifies a gas limit and a gas price, and you multiply the two to get the max amount of ether that the sender is willing to pay. Here's a quick example that we can run through to conceptualize this. Wow, you had a $50 transaction fail recently? That's crazy. DeFi, decentralized finance, has been really raising the gas fees high. So yeah, that's kind of an example of how this affects users. So let's go through an example. Say the gas limit is 50,000. The gas price is 20 GWay. So the maximum transaction fee is 50,000 times 20, which is that really big number, which is 0.001 ether. So for the transaction to be executed, the user has to have enough ether in their account to cover 0.001 ether. And the gas limit has to be enough to execute the transaction. So you do that, and then if you have unspent gas, it gets sent back to you. So this is the kind of diagram. You have start gas, you start the transaction, you keep on using gas as the operation goes on, and then when you end the transaction, the remaining gas is sent back to the sender, and the receiver gets the contents of the transaction. I really like how literate all of you are in DeFi. That's cool. If you should post on Piazza. You should talk about DeFi on Piazza and get the rest of the class in the loop. How fast are okay, one sec. Sorry about that. So how fast are transactions? Yeah, it depends on how fast you're willing to spend. It does take some time though. It takes up to 30 minutes to even to like an hour if it's really bad. But again, that's not a fixed amount of time. That's based on the network traffic at the time of transaction. And the Ethereum community is trying very hard to solve this problem through layer 2 solutions to try to scale Ethereum's throughput. So what happens if there's not enough gas to execute the transaction? The transaction will run out of gas and therefore is considered invalid. If the state changes are reversed, the failing transaction is recorded and the computation was already expanded, so none of the gas is refunded. So that's the key here. It's like a car. If you want to go to LA, but you only have half a tank, you don't magically get transported back to your starting destination if you run out of gas. You just are stuck. So That's why it's called gas. At least that's what I interpret it as. So cool. Wall Street bets, that's funny. What is the causes for rejected incorrect shares in mining? I'm not quite sure what you mean. Do you mean shards or shares?
Oh, no, I mean like you mentioned how when you run out of gas in a transaction, it's invalidated. Is that what results in an incomplete or a rejected share on miners?
Yeah. So that, yeah, exactly. So then the transaction wouldn't go through, a revert state would happen, and then the miner would have an incomplete share of the gas fee, and then you wouldn't have your transaction go through. So it's a lose for everybody pretty much. And for Rohan, your question, could you pay more to have your transaction occur faster? Yes, you could. You could like front run someone else and pay more gas fee to have it go faster. But even if you do that, it's still a marginal increase because it still depends on the network's traffic. That's still the biggest variable. You can't like, unless you pay like an exorbitant amount to go to like the very top of the queue, like it still largely depends on the network's traffic. Cool. So miner incentives. This was the original question. Where does the fee go? The fee goes to the miner's address as they have used their computational effort to validate the transaction. So that's the incentive to contribute to run nodes on Ethereum, is to get gas and mine Ethereum. So miners can choose which transactions to validate or ignore, and different miners have different strategies based on their own hardware to maximize their profits, basically, because they might have like special GPUs that are really good at certain tasks, and they can try to like code their own algorithm to choose which tasks to take or not, which actually is really tough because the code is hashed, but that's besides the point. But the greater the gas price the sender sets, the more likely the miner is to select the block. So it's a probabilistic thing, right? Because it's a distributed protocol. It's all based on just probability that your transaction will get picked up. So it's not like a fully guaranteed curve of how fast your transaction will go. Okay, so questions. The total amount of gas in the entire economy must be limited then, right? There's only so much hardware that can process transactions. So it's not limited by any hard number. It's limited by the hardware in the network. So that's why sometimes the network is slow, is because there's more transactions than the miners can handle. So a line kind of forms. It's like, that's the bottleneck, right? If the transactions are trying to like flow transactions through the network, the bottleneck is the miner's power. So if there's too many transactions, it'll just go slower because there's less workers to like complete the transactions. So yes, a miner's role is to validate transactions and perform computation for you. And they're the ones that essentially keep the network running. So they're mining your gas fees essentially. And they're very important because if they didn't exist, Ethereum wouldn't exist either.
Wait, I just wanted to clarify my question actually. I just meant about like total gas in the system. I mean like literally like total gas in the system, right? Because where does the gas originate from? Like I send it to you, you send it to me, you send it to someone else. Like there has to be like gas has to be like, you know, originated from something, right?
Yeah, so just like Bitcoin, there's a max amount of ether that is like set into the protocol. I actually don't know how much it is. I think it's like 100 million or something, but it's like that. So economically, there's like that much ether that will ever be released, and then it's a similar economic system to Bitcoin insofar as like the miners also get to mine ETH, and that's how its new Ethereum is introduced into the network, into the ecosystem. Yes. So moving forward, storage fees. So how does things get stored? Gas is used to pay for storage, and it's proportionate to the smallest multiple of 32 bytes used. So increased storage increases the size of the Ethereum state on all nodes. So if you're storing like images on Ethereum directly in Solidity, that's going to really drive up the price of your contract. So this is the incentive to keep the data small. That's why when you're building your dApps, you don't store anything on the blockchain unless it's completely necessary. Unless it's like the key thing that identifies something in the app, or it's one of the most important sensitive pieces of information that need to go on the blockchain. And we'll talk more about how to make the decisions of what goes on and what goes off chain. That's the real intuition that you're building in this class. When we're designing our applications, that's the intuition that we're building, is what do we put on the chain and what do we keep off? There's a question. Okay, that's not okay. So good. That's Ethereum high level overview. Again, check out the fundamentals lecture. We'll email you the links and we'll post it on the website if you're watching asynchronously. So that's the high level. Now we'll go into kind of smart contracts, which is more focused on what we'll be doing in the class. Yeah, and before that, I'll answer this question from Miles, which is, what is a miner able to see when they're processing a transaction? They can't extract any information, right? So that's a good question. I actually should know the answer to this, but my basic understanding is that they don't get to see they don't really get to see like anything too special. But keep in mind that when you make a smart contract on Ethereum, that contract code is public. So once you deploy, anyone can see the code. And that's what makes it decentralized and open source. So even these businesses that are sprung up around Ethereum, like all these Aave, Compound, all these DeFi businesses, all of their smart contracts are publicly available on like Etherscan. So if you go to etherscan.io, you can actually see the code for all of these contracts. So there's nothing like really special that the miner can see that a normal person couldn't see. And in terms of like what people can see for an account, like you can see an account's balance and stuff. So that's why blockchains like this are pseudonymous, because if someone knows your public key, you don't necessarily have a way to stop them from tying that public key back to you. Are DeFis used? Yes, there are millions of dollars of volume going through these DeFi protocols, and it's only going to go up, especially as platforms like Robinhood and E-Trade have literally turned off trading because their buddies in the hedge funds are getting ripped off. More people are going to start using decentralized finance products because they don't want their trading to be restricted. There's two questions, and then I'm going to continue after these two questions. But why would someone store on the blockchain rather than AWS? Are they similar? So that's a good question. They are not entirely similar. So AWS gives you like a server where you can, like an EC2, you can like run a program, you can run computation on that server. That's like your server to use, and you can like do whatever you want with it. In Ethereum, you're not really trying to do the same thing there. You're not trying to like host an app on Ethereum. Even if you make a blockchain app, you would probably still host the client on AWS. But that client would be the portal into the Ethereum network. So you're using Ethereum as a backend data structure to connect to people all over the world. So it's not really the same. I hope that kind of clarifies. Is there any way to store data on a blockchain privately? On a public blockchain, no. And that's the point. Cool. Okay, let us continue. So how do you actually interact with Ethereum? How do you use it? That is through smart contracts. So we have a normal contract, which is like a spoken agreement that's intended to be enforced by law. And let me turn off my notifications. So a smart contract is like a normal contract, except it's code that enforces the law or enforces the negotiation of a digital contract. So it's basically like whatever agreement that you would have with a person, you can write that agreement into code, and then you can rely on the smart contract code to execute that agreement. So say you and I agreed to have like a bet with each other, and like the outcome of the bet, like we'd flip a coin, and then whoever flips the coin gets the pool of money, whoever wins. We could obviously come up with the rules ourselves, agree on it, and then like, I don't know, execute the bet and maybe rely on someone else to like hold the money in the meantime. But with a smart contract, we can just plug that into a code on a smart contract, and then we can rely on the smart contract to do that negotiation for us. So in Ethereum, smart contracts are like autonomous agents that live inside of the Ethereum network. You can poke them like an API call. You can poke them with the transaction with specific functions and parameters and then you can use the contract to change things in Ethereum. So contracts have direct control over their internal ether balance and their internal contract state. So you can store variables in contracts. So Ethereum contracts serve 4 purposes. One is that they store and maintain data, and that data is useful to users or other contracts. And so an example of this is like a token or an organization membership. Like you're only a part of BAB if you like if your name is on this public contract. That's a good idea, honestly. We should do that. Another idea is like you manage a contract relationship or relationship between untrusting users. So financial contracts, escrow, that betting program that I just mentioned. A third thing is that you provide functions to other contracts. So contracts exist that are libraries. So Open Zeppelin makes a safe math contract so that they've already created like just like you import Python, import math, Open Zeppelin has created like a safe math that you can import and just use. And they've worked around all the security features of these contracts. And then the fourth thing is complex authentication. So there's things called like multi-sig wallets, multi-signature contracts. So this is like a cryptography thing too, but like if you have N people, you only need M of them to like access the contract, access the account, change a transaction. So you can set things like this up too. And that's because of the cryptographic nature of blockchain, really. So one more question is it easy to use smart contracts? Do you have to be a developer to make use them? So I guess naturally, since it's code, you have to be a developer to write the code for the contract. There are no code tools that are emerging to create smart contracts, and there will be more of those in the future. But to use a contract, ideally, no. Like, it's not supposed to be restricted to developers. It's supposed to be for everybody. Obviously, that's a big thing to say because it's very hard to create a good user experience for a user who doesn't really know much about blockchain. They have to like log in with their wallet, and then they have to like think about these things that they haven't thought of before. But once the global kind of world starts to use these things, maybe the next decade or two, then it'll be just like using your phone. Like no one's going to think about it more than just like using your phone. So no, you don't have to be a developer to use applications that have smart contracts in them. And Callum asks, how does copy and pasting compare to poking libraries in terms of gas costs? So it's like the same thing. It's like if you import a library in Python or C, you're just going to use the code from that library. So it's like the same amount of gas cost that would happen if you just wrote it yourself as well. Yeah. But in Ethereum, there's a lot of optimization that goes on, right? So if you use a library to conduct some like advanced thing, it's very likely that the library that you use has been optimized by really good engineers. So you don't even have to worry about the gas cost because like they've tried their best to reduce the cost. Whereas if you wrote it yourself, like you probably would not take the same approach that they did because like this whole community is so open source and it's so based upon composing different things together that everyone just wants to make products that we can build up on each other. So it's really good that way. It's all open for everyone. So continuing on, I think we are okay. It's 7:08. We've timed the lectures to be around 1 hour 30-ish. So I think we're almost kind of wrapping up. But Ethereum smart contracts, some important things about them is that they're immutable. Caveat this by saying that like it's immutable based off of the system's assumptions. There are obviously attacks that can happen, like a 51% attack, but the idea is that they're so improbable because of how hard it is to do them. So they're immutable, no tampering post deployment. You can't change the code of a smart contract post deployment. You can upload a new contract that has updated code and then send to all the clients that they have to point to the new contract instead. Like that's how people handle upgrades on Ethereum. But an actual contract is deployed. It's like compiled code. It's like a Docker. You can't like change it. And it's public. As I said, you can request source code and compile that source code yourself. So it's really as easy as going to the website, entering the address, and you get all the code. So if you want to start a business, you don't have to like guess at what they're doing. You can go to the most popular like lending platform and literally get the code from them and then make the changes you want. Like that's a very it's a very common thing. Can we get Vitalik to come talk? I've talked to Vitalik once, so maybe he remembers me, but I doubt it. So okay. Yeah, so these two characteristics ensure that there's trust in the smart contract system. Okay, so now let's go into some code. This is a code of a smart contract. So this is a betting contract, and I'm pretty sure we use this in the blockchain at Berkeley like interview process. But there's a couple things here to look at. There's addresses are their own data type, and we'll learn all about this Solidity stuff in lecture 3. So I'm gonna just talk right now. Don't necessarily feel like you have to understand this whole code. But you know, addresses are their own data type. So there's an owner, there's two gamblers, and an oracle. The oracle is like the person who decide, or like the contract basically that decides what side won. There's an array of outcomes of unsigned integers. So you can also store structs in Ethereum. So this is a betting struct with the outcome amount and if it's initialized or not. There's mappings in Ethereum. So mappings are very important because that's how, because if you think about it, a blockchain is made for telling people who owns what. A mapping is a mapping from people to what they own. So it's like a pretty intuitive data structure that we use in Solidity. So mapping from addresses to bets to winnings. Comments are there to make it clear. Oh, couple functions here. So make bet, make decision, withdraw. So payable is like a type of thing too, as well. Oracle only. So these get more convoluted. You'll learn about them over time, but this is kind of what a contract looks like. This is like an interface for a contract. So what runs the code in these contracts? So there's an EVM, which is the Ethereum virtual machine. It's like a mini computer that runs contract code. And this contract code is actually executed on every node the contract code that gets executed on every node is EVM code. So this is like compiled code. It's low-level stack-based bytecode language. So like Java bytecode, it's like the same kind of thing. So yeah, it's like a compiled language. Now let's get into designing Dapps, Dapper Labs. So Dapps are implemented via smart contracts. They're peer-to-peer with no central server. They're immutable. They're open source and transparent. And they're similar to traditional applications, but they're decentralized. So in a traditional app, you communicate through your internet service provider, through your Wi-Fi, to a data center. So that data center could be distributed. YouTube has servers all over the world, but it's still YouTube servers. It's still run by Google. DApp is different because you communicate with a random node run by some person. It doesn't really matter who. And you communicate with the contract through that. So it's much more peer-to-peer. Yes. So workflow, DApp development process. So you get it right the first time. You have to. We'll use test-driven development. It's a good word around Silicon Valley and Berkeley. It can be compared to hardware development as opposed to traditional app development. You'll kind of see why later. Simon wrote this, and he's a big hardware guy, so I think that's his take, and I'll explain that. So there's more information on the current state of Dapps development. That's good, a good link to check out as well. But the reason it's more like hardware is because you have to build from the ground up for security and for proper like execution. You can't like start coding you can't just like barf Python onto a paper, or you like with Python you can just like kind of like just start coding, putting things down, and then change it as you go. But in Solidity and in blockchain development, you have to like think about the entire system first. What is this? Okay, so backend is the development of the core functionality. So exactly, this is why it's like hardware. You start off at the low level. You start off with the smart contract. Then you test the smart contract. Then you start thinking about how the user will interact with it through the UI. Then you go into integrating the UI into the smart contract, and you do all the testing. Then you go onto a test net. So Ethereum has the Ethereum mainnet, but there's also 2 or 3 Ethereum test nets that you can use first to deploy. And next week, we'll be getting a guest lecturer that will describe the industry standard workflow for how to develop these apps. You should come next week. That is going to be an amazing lecture. So yeah, that's the workflow. And then once that all works, you've tested at every stage, you deploy to mainnet. What a beautiful slide. Wow. Okay, don't worry about this. We're not taking attendance this semester, and that's not updated. So, okay, any questions on that? We could develop an optimized miner. That's a big project. I think that'd be a cool project, developing an optimized miner. So like there's different optimizations you could do. If you want to chat about that, just like email me. That's like pretty cool. Okay, so no other questions. I know that was a lot. There's still a little bit more content to get through. These lectures will be a bit dense because blockchain is its own beast. So we have a lot to get through every time. I'm trying to keep it exciting. So hopefully we can get through it. But yeah, and arbitrage bot's also very hard, but I can give you tips if you want advice. Okay, so the first homework is one of the coolest homeworks I've ever seen. It was written by Omkar, who graduated, so congrats to him. You will be able to basically spin up your own blockchain in Python in an IPython notebook. So it's uploaded on the GitHub, homework 1. I'll make sure to, yeah, until I get it ready. I think it's already ready, but yeah, you're basically going to go through a Python notebook, and then we talked about a lot of stuff today, but you'll get to see exactly how a blockchain is made. And this is going to be like your fundamentals crash course. So what we'll do now is go through a fundamentals crash course so you can do your homework. So yeah, let's get into it. How's everyone doing? I see people have video on. That's awesome. Good to see you guys. Yeah, I'm gonna take a quick break and sip this boba. So feel free to ask any questions. Yeah, kind of baffled. It's a lot. It definitely is a lot. No worries. Okay, let's just get into it. Yeah, let's just go. This part is pretty good. So this part blew my mind when I was a freshman taking this course. So let's get into it. All right. How does blockchain work? There's 2 main concepts that make blockchain work. One of them is cryptography, and the other one is consensus. So if you understand these 2 things, you can understand the intuition behind blockchains. So let's go over cryptography first. And if you've taken 61B, taken 70 or CS 170, this will be very easy. If you haven't taken it, then some of the intuition might be a little bit harder to grasp, but this is a great way to just introduce yourself to it. So how do we ensure trust in a communication environment where there's no trust? We use hashes. So a hash function has 3 special properties: pre-image resistance, second pre-image resistance, and collision resistance. So pre-image resistance is, so if you look on the right here, there is the pre-image is I am Satoshi Nakamoto 0, 1, 2, 3, 4, 5 up till 19. And then you hash it and you get the hash of these things. So a hash is a one-to-one function that takes in an input and then gives you like a unique output that is unrecognizable to the input. You can't reverse a hash. Like you can't take this string A808811401 and then somehow figure out that, oh, that means I am Satoshi Nakamoto 0. Like it's very, even if you know the hash function that was used, you can't like reverse engineer that. It's impossible. So that's the point of a hash function. And that's what pre-image resistance is. So collision resistance as well is its own thing. So based on the hash function that you're using, you don't want any 2 inputs to map to the same output. Sometimes this happens because like it's based off of probabilities, but you want your hash functions to be collision resistant, basically, so that there's no overlapping inputs. And how do we use hashes to verify things in a blockchain? We use a Merkle tree. So you'll be actually implementing, or I don't know if you're not going to implement it, but you're going to like see a Merkle tree in your Python notebook for your homework. And I want you to know what that is before you do the homework. So this slide is in black because it's like a very technical slide. So that's why we make it black instead of white. So say you have your transactions lined up on the bottom of this tree. That's what a Merkle tree is. It's a list of transactions that hash upwards into a single Merkle root. So say we have 4 transactions, we line them up, and those are the leaves of our Merkle tree. We then take the hashes of those transactions here, and we hash pairs of transactions until we get to one single tree. So the height of this tree is log 2 of number of transactions, because we just divide by 2 every time, and then until we get one thing. So this Merkle root is really important because, as we saw, a hash is a very sensitive function. Even changing Satoshi Nakamoto 0 to 1 completely changes the output of the hash. So if any of these transactions change even a little bit, the Merkle root will completely change. So we use that property to ensure tamper evidence in a blockchain. So let's trace this all the way. So this goes transaction 1, hashes together, all these things. I don't really know what the point of that was, but the point of a Merkle tree is that it's tamper evident. So if any one of these TXs is altered, the Merkle root is altered as well. And that's important because in a blockchain, the block header has these 3 components. The previous block hash, that's what makes it a chain. So when you see the classic image of like block pointing to block, pointing to block, the pointer is this previous block hash. So it's the hash of the previous block header. So that's what makes the blockchain. It's like that. It's the hash of the previous block header. A nonce, which, as I explained before, it's like a security feature. In this case, the nonce is the solution to the proof of work puzzle. Do not worry about that. But importantly, we have the Merkle root. So the Merkle root is what verifies the contents of the block. Okay. So yeah, as I said, blockchains are tamper evident. So we use SHA-256 in Bitcoin. The previous block hash is the hash of the previous block hash, the Merkle root, and the nonce together. So that is the pointer to the previous block. And yeah, so if you look at the middle one here, this Merkle root is tampered. So the previous block hash, the hash of this tampered Merkle root will also be tampered. So in this case, the block header is tampered, And the blockchain will know that this block is not an honest block because it doesn't compare to the rest of them. So basically, that's how we keep it. So we keep it honest using cryptography. That's how we don't have to trust anybody. Okay. So what is the block header? The block header is basically the identity of the block. It's not like an address necessarily, but like a linked list, it's like the identity of a block. And its identity consists of those three parts, which is the nonce, the Merkle root that we discussed, and the hash of the previous block. So that's what makes it like a linked list, like a chain. Cool. So now let's talk about mining, finding a valid nonce. So this is pretty complex, but you want to solve the proof of work. You expend computational power and you find the nonce. So what is a nonce? In proof of work, there's something called a target, and you want to find a nonce that is below the target. And that target goes closer to zero as every day goes by. So it gets harder and harder to find a nonce between 0 and the target. But once you find one, then you solved it. So you solved the proof of work. And that's what your nonce is. It's the solution to that proof of work. Yeah, as I said, there's a target here, Coinbase, nonce, while true, just do all this hashing, keep on double hashing all these things with the random nonce to make sure that you found a block. That's basically it. So yeah, I'm gonna skip this slide. This is just a hash puzzle. Like, that's fine. So yeah, so now talking about the homework again. In the homework, you're implementing different aspects of a blockchain that we understand. So you'll be creating a blockchain type data structure using object-oriented programming. And you'll be creating your own kind of proof of work simulation. So this will kind of help you understand the concept of why it's hard to find the next block. And you'll simulate multiple miners competing to find the next block. And you'll see how it plays out when there's different levels of computational power. So we have some data analytics code to see what we've implemented and if it makes sense as well. So yeah, to get started, we'll send you the repository, Spring 20 dev decal, and you just clone it to wherever you do your schoolwork. You should probably clone it. Downloading the zip is kind of lame, but clone the repo and then go run through the notebook. For submission, we are just going to have a Google form. So you submit the PDF of your Python notebook that's completed. So just like, yeah, go ahead and complete it. Ask on Piazza if you have questions. I'd be super happy to host a homework party or some kind of like synchronous collaboration party. Just post on Piazza. Let's get the Piazza poppin'. Talk about DeFi. Talk about any random thing. You have access to all of the Blockchain at Berkeley staff to talk with you about stuff. So any random idea you have, just post on Piazza. It'll be a good time. And I'm pretty sure that is it for today. So yeah, cool. So are there office hours, Solomon? Do we have scheduled office hours yet?
I don't believe we do, but we can look into it.
Okay. Yeah, for now,
I think that's a good idea for sure.
For sure, yeah. For now, just use Piazza. We will definitely create some sort of synchronous FaceTime so we can talk, but really appreciate y'all turning your video on and hanging out with me for this hour. I love lecturing and stuff, so we're gonna send out the codes sometime the next 2-3 days as well. So yeah, that's that. Cool. So I think we're good. Solomon, let me know. I'm gonna stop recording.
Yeah, I think we're good here. Thanks for attending the first lecture, guys.
Yeah, and come next week. Definitely come next week.
Thank you, guys. Thanks for taking the time. Have a good one, y'all.
Thank you.
You too.